Hi, this is Mr. Beckstrom, and we're going to be talking about the Section 7.3 objectives, and this is specifically understanding the histogram of the sampling distribution of the sample mean. So a lot of words, but basically what this does, it allows us to find a mean and a standard deviation when we're talking about a distribution of sampling means. That means if we take a group, instead of just one person, we can convert both the mean and the standard deviation to allow for more than just one individual or object of our data set. So let's take a look at this one here. So this is the number of used cars sold in a summer week at Alley's. Auto has a population distribution as shown in the probability histogram below, and the population mean is also given. So they're not giving us the population standard deviation, but they don't really need to in this case, because the important part is that since this is a normal distribution here, it doesn't matter what sample size we have. The sample size or the distribution of the sample means for any sample size is still going to give us a normal distribution. It'll still give us this normal curve. The only difference is going to be the standard deviation. So the mean will actually stay the same at 1.82, but the standard deviation is going to get smaller. So we're going to be looking, instead of starting at 0 and going to 4, we'll be starting somewhere greater than 0 and ending somewhere less than 4. It's going to be kind of squished together. So let's see the possible answers here. Remember, a mean of 1.82. So this one is pretty close, and it does start somewhere after 0 and ends before 4. So that's the one I'm leaning towards. This is a left skewed distribution, so that's definitely not right. And this is a right skewed definition histogram, or distribution. So this one is definitely not right. So we're going to stick right here. For this next one here, it says size of n is equal to 7. So now we're getting up. So we should expect something like this, same mean, but it's going to start even later than this, like 0.5, and end somewhere less than this 3.5. So let's take a look. So notice that the mean is not anywhere near our population mean, so that's not going to be it right there. This one is also pretty far away from our 1.82 mean, and this one is right there at about our 1.82 mean. And notice that 0.5 is here and 3.5 is there, and this thing is squished more together. So that is our answer. And finally, size 30. So let's take a look at this one. Again, same mean, but the only thing is it's going to be squished together even more. So let's take a look at the three possibilities. This one has a mean that's greater than 2.8, so that's definitely not the right one. Here, this is looking pretty good. It has a mean right about where we want it, the 1.8, and it starts about 1.4 and ends around 2.6. So it is squished together relative to the last one. And this one here, no, that mean is not at 1.8. So definitely going with this one. And that's it for starting with a normal distribution. Let's take a look at one where we're not starting with a normal distribution. Okay, so for this one here, it says the number of days with snowfall in a year in Pleasant Valley has a population distribution is shown in the probability histogram below. The population mean is also given. So the average number of days with snowfall is just a little bit over 2 days. And notice we do not have a normal distribution here. We have a left skewed kind of distribution. So in order to be able to use our definitions for the central limit theorem, which is the average of the sample means and the standard deviation of the sample means, we either need to start from a normal distribution, like we did on the last problem, or our sample size has to be greater than 30. And until we get a sample size greater than 30, it's our our average of the sample means and our standard deviation of those sample means, it's going to look a lot like this original one with a mean. It's kind of hard to tell where the mean is because this isn't normally distributed, but it's somewhere just above 2 here, so right about there. That means there's the same amount of area on both the left and the right of this value, just over 2. All right, so for the first one here, this one is skewed left, and it looks like that pretty well divides both sides. So this is the one I'm leaning towards right now. This is a normal distribution, which we're not going to see because the sample size is only 3 and it needs to be greater than 30. And finally, this is skewed right, whereas our original is skewed left. So it's definitely not this one here. So we're going to go with this one right here. Now remember, the larger n gets, the more that we should get something resembling a normal distribution. So this one has a sample size of 9. So let's take a look at the possible values. Our mean is 2. So here this looks good, but this is definitely not the mean. So this is not the one we're going to use. This one looks pretty good. It's just slightly skewed to the left, and the average or mean is right where it should be, just over 2. And this one is definitely wrong because the average is nowhere near 2. So this is the one we're going to choose for that. And then finally, how about a sample size of 30? So now that we're at the 30 range, this thing should really look like a bell curve, symmetric on both sides. So we have this one. Unfortunately, our average is 2, so that's definitely not near this mean. This one looks like a 1.5. Again, the mean here is nowhere near that 2. And here, yep, it's right above 2, very symmetric on both sides. So this is the one that we're going to go for. And check. And look at that, all correct. All right, guys, if you have any questions, please let me know. And I hope you have a great rest of your week. Thanks.